Right. Okay. So we are going to solve one more example in the 2D advection diffusion case. Okay. So this is a very interesting example and it helps us understand the concepts even more. Okay. So this problem consists of a domain of size 1 by 1. Okay. And so the boundary conditions are such that, okay, so here on this edge from 0.2 to 1, we have a non-zero Dirichlet boundary condition, that is here u equal to 1, and on this edge, like shown in as a thick black line, so we have a 0 Dirichlet boundary condition. Okay, and we have a advection in the specified direction. Okay, so we have this advection vector in the specified direction. Okay, we consider the magnitude of advection vector as 1, and we can take different angles theta, and we can also study for different values of the viscosity, sorry, or diffusion coefficient. Okay, I don't know why I keep saying viscosity, but yeah, the concept are more or less the same. So okay, so this is like diffusion coefficient. Okay, so we can study for different angles, different diffusion coefficients for a constant magnitude of advection velocity. Okay, with this boundary condition. So for if like for what happens is, so we have a specified value of 1 here and 0 here. Okay, you see, so 1 here and 0 here. Okay, so we see a significant, like a sudden jump. Okay, there is a discontinuity here, and this develops into, like, so this, because of the advection, this develops into a clear discontinuity, and depending upon the direction, the discontinuity like shifts in the domain. Okay, so depending upon the angle, so it moves towards this edge, but we still see the discontinuity, and that is the jump in the solution. So this is a very difficult problem to solve. Okay, and we will now see if the whatever we have used so far helps, and if not, what are the alternatives. Okay, so I'm going to create, like I have created a domain in Gmesh. Okay, and I have created domain such that I have a separate line, okay, separating these two boundary edges, because we need a value of 0 here and here, and a value of 1 here. This is a 100 by 100 mesh, but I also have some other like coarser meshes with 20 by 20, 20 by 20 and 40 by 40. Okay, so I have boundary flats. Okay, so bound 1, bound 2. Okay, so boundary 1 is this one, these two boundary edges, so where we have a value of 0, and bound 2 is this boundary, so where we specify a value of 1. Okay, so I have created those three different meshes with 20 by 20, 40 by 40, and 100 by 100. I have saved the file, the main file. Okay, so the main loop where we loop over the elements and where we have all the information about boundaries arrays. Okay, I have copied it and I have saved as example2. Okay, a new file. Okay, so let's keep our viscosity, our diffusion coefficient at 0.001. Okay, and we don't have the force here, so F is 0, and we start with an angle of 30 degrees. Okay, theta is 30 degrees, so pi by 6. Okay, so the advection velocity is one cos theta and 1 sine theta. Okay, so to start with, we turn off the stabilization. Okay, so we get all the boundary terms, all the boundary nodes. Okay, so all these boundary nodes, but the value is not the same everywhere. So we need to add some code to specify that the solution along this boundary or all the nodes on this boundary is 1, is specified to be 1. Okay, so what am I going to do? I'm going to add a loop over the lines okay, so loop over all the lines, and then okay, and then we check okay, so let's check the mesh file. Okay, so we have the nodes. Okay, these are our line elements. These are the boundary like two node line elements with the flats at the third index. Okay, so we check the third value, and if it is 2, okay, remember, so for this boundary the flat is 2. Okay, if it is 2, then we need to do some calculations. Okay, then so for these boundaries we get node numbers. And since we have only 1 degree of freedom per node, our node numbers become our degrees of freedom, and then we can use the node numbers, okay, and specify that the solution is 1 on those nodes. Okay, so this is the major modification that we need to do for example 2, because our boundary conditions are different. And don't forget to change f to 0, because there is no boundary term, sorry, there is no body force term. Okay, and everything else is the same. We don't need to change the stiffness matrix. Okay, but we start with the stabilization factor of 0 to see what happens with the pure Galerkin formulation. Okay, I'm starting with the 20 by 20 mesh. Okay, so this is the solution we get. Now, okay, so there are some oscillations. We see a clear jump in the solution, but the jump is not really sharp. Okay, because the mesh is coarse. And we also see some spurious oscillations here. Okay, they are not really like quite drastic, but we do see some jumps, some oscillations. Now let us see what happens if I change this to, okay, so now we have 1e minus 3. Okay, I'm going to change this to 1e minus 4. Okay, so now the oscillations got bigger. Okay, well, let's say with 1e minus 5. Okay, so as we expect, the oscillations should get worse. Okay, as and they do. And let us see what happens if we use a finer mesh. Okay, so example 2, I'm going to use a 40 by 40 mesh. Okay, so there are still oscillations. And with a 100 by 100 mesh, okay, this takes a little while because the mesh is fine. So we have about 10,000 degrees of freedom. And I'm using a dense matrix algebra, so it is a little bit more expensive. Okay, we have the solution. Okay, so with the finer mesh, we do see, right? Okay, so we do see sharp discontinuity, but we still have oscillation. So that means the mesh is not good enough. So, okay. So we want to get accurate solutions with coarser meshes. We want to get rid of the spurious oscillation. That is the main thing. So we turn on the stabilization and we switch back to the coarse mesh. I'm not sure what's happening here. So I think I have some mistake here. Okay, let me check. Yeah. Okay. So the mistake is I am getting all the numbers in these lines, but we should only get the node numbers. So we should get only the first two columns, right? Okay, for the node numbers. Okay, so I'm correcting this here now. Okay, so we got rid of this mistake here. Okay, now we also got rid of the oscillation because of the stabilization. Okay, so this is not an oscillation, this is the Gibbs phenomena. Okay, we got rid of the oscillations, but the solution is like it is smooth, but it is still not exactly correct. Okay, so this is because like I don't know if you're familiar with the Riemann problem and all. Okay, so well, since we are using a linear formulation, it is impossible to get the solution without violating this condition, that is the solution is not bounded. Okay, before we discuss that further, so let's use a finer mesh. Okay, so the solution is free from spurious oscillations. The spurious oscillations it is free from spurious oscillations here, but the solution is still has some jumps and like undershoots and overshoots. And what happens with if you use the finest mesh? Okay, the solution has a steep jump. Okay, but we still have some undershoot and overshoot because the value is above 1. Okay, so we can also like we can also generate meshes with a refinement along the boundary layer or along the jump. Okay, so this is a mesh. Okay, so let me show you. Okay, so what I have done, I have created a line. So along the jump, okay, so I know that there is going to be jump along this line. Okay, this is kind of cheating, but it helps you demonstrate the refinement like property. Okay, so what happens with the refinement? So what I have is, so you see here the mesh is coarse here and it is fine here. Okay, so with you by selectively refining the mesh, we can improve the accuracy. I think I have even a finer mesh. Let me run and check. Yeah, so this is even a finer mesh. Okay, so yeah, here as you can see now, okay, there are still some like undershoot, overshoot, but the solution is better. Okay, so okay, so with the right, okay, so with this we start with this diffusion coefficient, that is 10 power minus 4. We got a really good solution, okay, with adaptive refinement. Okay, now we don't have any undershoot and overshoot. That means, so the mesh is sufficient enough and the stabilization is sufficient enough to get like accurate solution for this problem. But as soon as we reduce the diffusion coefficient further, that is increase the Peclet number further, it is not working. So that means like the although stabilization helps getting rid of the spurious oscillations, we still don't get the correct solution using the SUPG method. Okay, and let us change the angle. Okay, so now we change the angle from 30 to 60 degrees. Okay, so with this, the adaptive refinement is not the refined mesh is not good enough. So because we have the refinement at a round place. Okay, in this case, with 60 degrees, the jump would be here. Right, this point would be here. Okay, yeah, see. Okay, yeah, we do get good results, but they are still not perfect. Okay, so the reason is that this SUBG stabilization, although it helps us get rid of the spurious oscillations, it doesn't help in preserving the bounds. Okay, it is primarily because it is a linear stabilization method, and as you know from the Riemann problem, okay, and yeah, so we need to add. Okay, we need to add some additional stabilization. Okay, so SUPG is a linear method. It is less computational effect. It helps removing spurious oscillation, but the solution is not monotonous. Monotonous means like it is within the bounds. We do observe some overshoot and undershoot, also known as Gibbs phenomena. Okay. So in order to overcome this issue and get a accurate solution, we need to add additional stabilization, further sophisticated method to remove these overshoots and undershoots. So there are a lot of sophisticated stabilization method. For example, subgrid scale stream or and positivity preserving streams. Okay, we also have this short capturing streams which do preserve positivity, that is make sure that the solution is monotonous, but they become complicated because the formulation becomes non-linear. Okay, so for example we can add short capturing streams or short capturing terms. Okay, so here I'm not going into the details, but this is a like just brief about sharp capturing term. Okay, so this sharp capturing term, so this is similar to the diffusion term. Okay, as you can compare here. So this is our original diffusion term of like in the weak form, and this is the sharp capturing term. Okay, so this is very similar to diffusion term, but with a new parameter. This is the sharp capturing parameter, sharp capturing term delta. Okay, so what we do here is we add an artificial viscosity, artificial diffusion to the formulation to minimize the spurious oscillations. Okay, so this is the sharp capturing viscosity, okay, delta. Now the key step in sharp capturing terms is to come up with the method or to come up with an expression for delta that ensures convergence and accuracy. Okay, there are a lot of varieties of short capturing terms with various expressions for delta, things that are really complicated. We do not need this for incompressible flows. Okay, but we must use this if we are interested in solving compressible flows, because in compressible flows we do like we do see short waves with like where we have high pressure jumps, density jumps. Okay, so this it becomes essential in compressible flows, but since we are interested in incompressible flows, this is not of primary importance for us. Okay, so I'm going to leave this to you if you are interested in compressible flows. So like you can leave a comment if you want references for this. Okay, so with that we conclude this lesson. Okay, and again, if you have any comments, if you find any mistakes, please leave a comment, and I do appreciate your feedback. Thank you.